every one of us who have been working in this area knows about John. So, so as John is not only a very, very good researcher, as we all know, but he's also an excellent teacher. And that was one of the reasons we thought that we should invite John over here, and it's also nice to see him after such a long time. So I am not going to stand between you and John. So I think that we are off to a fantastic start with these set of lectures by John and Professor Anders Sandvik. So I hope that we all get to learn a lot in this series of lectures. So I'm not going to stand between you and John. John.
Okay, so good morning, everyone. So I'm extremely happy to be here. This is my first visit to Chennai, and so I'm very grateful to the organizers for inviting me. So in these lectures, I want to give an introduction to frustrated magnets, and I hope at a level that will allow even people who are not so close to the field to get going in the area. And I've planned mostly a Blackboard talk, so if you have trouble reading the Blackboard from the back, then you should probably move to the front. And if what I've written already on this left-hand side of the Blackboard is obscured by the podium, you might want to consider moving somewhere nearer the center of the lecture theater, because I think I will need to use all of the board. So this is an overview of the 4 lectures, and I want to start out by introducing some of the questions in theoretical magnetism, in frustrated magnetism today, and talk about some of the techniques in the second lecture that we can use to think about these models theoretically, particularly in the classical cases. And in the first lecture tomorrow, I'll talk about one of the particularly interesting examples that we have of frustrated magnets, which we can think about using the tools of classical statistical mechanics, which is known as spin ice. And then in the second lecture tomorrow, I'll start talking about quantum problems and quantum dimer models. So I should say it would be good if these lectures could be interactive, and if I say something that's not clear to you, then please do interrupt with questions, and I'll try and pause from time to time to invite questions. Okay, so I'd like to start off by using the Blackboard, so if we could have the lights on the Blackboard, that would be nice. I think the middle light was on earlier. Oh, I see, yeah. Okay, so if you start out by asking from a rather basic point of view what we're thinking about when we talk about frustrated magnets and spin liquids, you can ask about the term spin liquid, and it's pretty obvious that when it's used, one's making an analogy with the usual phases of matter. So usually we talk about a gas and liquid and solid as phases of matter, and there's an analogy with magnetic systems. and you can say that a paramagnet is similar to a gas, and on the one hand that's because it's a high temperature state of matter, and then maybe more importantly it's because just as the atoms in a gas have positions that are more or less uncorrelated, so the spins in a paramagnet have orientations that are uncorrelated. And then if we go to the other end of this analogy, the equivalent to a solid is a magnetically ordered system. So if we think about antiferromagnets, then we think about a Néel state. And again, the reason for the analogy is reasonably clear. It's a low temperature state, and it's got long range order. So the question is, how good is this analogy when we come to spin liquids? And the things that I want to stress at this stage are that the analogy is actually not very good, and in point of fact, spin liquids are much more interesting than ordinary liquids, or maybe that's my prejudice about ordinary liquids. Incidentally, we might want to distinguish here between classical liquids and quantum fluids. So by quantum fluids, I'd be thinking about a degenerate Fermi gas or a Bose gas that's got a Bose condensate. And then we could think about spin liquids. Either classically or quantum mechanically. And the ways in which this analogy is not so good are, firstly, when you think about correlations. So if you have some canonical example of a liquid, say a liquid argon, then you have some short-range correlations between the positions of the atoms, but at long distances, things are uncorrelated. Whereas in spin liquids, the interesting thing is that you have large correlation length. And in fact, the systems that we're interested in have a divergent correlation length as we go to zero temperature, as I'll explain. And in quantum spin liquids, well, I won't have so much time to talk about this myself, but you'll hear from other lecturers that although there's no order in the sense of a Néel state, we may have topological order, and we may have fractionalized excitations. And so the main reason why we're interested in frustrated magnets is that they help to promote this kind of liquid physics in preference to the long-range order that we get in unfrustrated systems. So any questions about anything at that stage? In point of fact, you can have frustration even with ferromagnetic interactions if you have terms in the Hamiltonian that compete with each other. And in the case of spin ice, I'll explain that we have competition between, in fact, ferromagnetic interactions and single ion anisotropy. And in the case of the Kitaev model, again, you can have competition between ferromagnetic interactions which couple different spin components. Yeah. Okay, so yes.
This condition for large correlation length, is that absolutely necessary to classify something as a spin liquid? There are spin liquids probably which are short correlation, like the cation model.
Yes, well here I was, there's meant to be a
Only for the classical.
read across. Yeah, yeah.
Lattices or something, they actually have short-range correlations, but they show some fractional excitations like orphans.
Yeah, I had particular things in mind, Coulomb phases, which, as you're pointing out, don't apply to all examples, but it's at least possible that you have something rather different from an ordinary liquid via this long correlation length. Okay, so to make sure things are clear, when I'm talking about frustrated magnets, I will always have in mind materials that are good Mott insulators, so that we can think of a lattice with well-defined local moments at lattice sites, and we can describe those systems using simple spin models, so Ising models or Heisenberg models, and things of that kind. Okay, and then the key point about frustration, as I mentioned, is that it destabilizes long-range order, and a lot of the rest of this lecture will be talking about how that happens in quite a lot of detail. And to get started, we can usefully think about a cluster of a small number of spins. So we might think about 3 spins which are interacting with each other on a triangle, or 4 spins on a tetrahedron. And more generally, we can think about a cluster of some number of Q spins. So Q equals 3 would give us a triangle, and Q equals 4 would give a tetrahedron. And I want to think about classical spins, so I'll take them to be fixed length, and to keep the discussion reasonably general, I'll think about n-component spins. So if n is 1, then this is not really a vector, it's a scalar which can be plus or minus 1, but if n is bigger than 1, then this is an n-component vector, and the degrees of freedom are the orientations of the vectors. So if we have a Hamiltonian which involves interactions between the spins in the cluster, then we'd write a spin model like that with J positive if the interactions are antiferromagnetic. And then a convenient thing to do for discussion is to notice that we can get interactions between all the spins in the cluster by, first of all, summing over the spins, and then afterwards taking the square. And the point is that if we expand this square, then we generate interactions between the different spins with a factor of 2, so the coefficient is j over 2. And normally we wouldn't include in the Hamiltonian an interaction of a spin with itself, so the diagonal terms in this sum would be excluded, whereas when we square the sum here, we include the diagonal terms, but the diagonal terms are constants if we keep the spin length fixed, so the Hamiltonian is just that plus a constant. And then the advantage of writing things in this form is that if we're interested in low temperature physics, then we're perhaps first of all interested in ground states, and so we want to minimize this Hamiltonian, and having got it into the form of a square, we can see that it's minimized when the argument of the square is 0. So you can ask yourself how many ground states you have in a problem like this. And if we had ferromagnetic interactions, so that this J was negative, then of course the ground states would be ones in which all of the spins had the same orientation, and the number of ground states would just be a consequence of symmetry. So in the case of Ising spins, the spins could all be positive or could all be negative, and we'd have the two ground states related by symmetry. But if we have antiferromagnetic interactions, then we have a higher degeneracy because of the frustration. So if I talk in detail about Q equals 4, then in the Ising case, that's one component spins. The ground states, well, to minimize this sum, I should have 2 spins up and 2 spins down. So one possibility is like that. And of course, I can take permutations. So I have 6 states, which clearly is higher than the degeneracy that I have simply as a consequence of symmetry. And if I go to n equals 3, then I need to find ground states by minimizing this sum, and I'm combining 4, if I take spins on a tetrahedron, fixed length vectors. So one possibility is an arrangement of spins like that in the plane. But I have choices. I can vary this angle, and I can also think of introducing an axis down here and rotating these 2 spins relative to the other 2 spins. So I have 2 ground state degrees of freedom. this angle and that rotation angle, in addition to the global rotations, which would give me a degeneracy even for a ferromagnet. Okay, so the basic point is that, at least at a classical level, and we'll have to come back and discuss fluctuations in a moment, this higher degeneracy gives us a chance of destabilizing the long-range order that you would have in systems with unfrustrated or ferromagnetic interactions. Any questions? The second one. Yeah, okay, so there's a background point that I should make, which I passed over. In the case of a system where we have discrete states like the Ising model, then when we discuss degeneracy, we simply want to count the number of states. In a system where we have continuous degrees of freedom, like the classical Heisenberg model, we can no longer count states, so we should count degrees of freedom or coordinates in the ground state. And in any model with Heisenberg symmetry, we have a degeneracy of the states corresponding to counting coordinates involving global rotations of the spins. We rotate all the spins together, and then if the spins are three-component spins with fixed length, we need two angles to, if it's a non-collinear state, we'd need three angles to specify the orientation. But the point here is that in addition to global rotations, we have some internal angles. So the picture I drew is meant to be a representation of a ground state, and in the ground state, the resultant of these four vectors is 0. So I'm drawing four fixed-length vectors which have resultant 0. And when I did that, I had two choices. One was the angle between this spin and that spin, and the other is whether I draw all four spins in the same plane, or whether I allow these two spins to be in a different plane from those two spins. And so the idea is that those two choices correspond to two additional degrees of freedom in the ground state. Okay, so continuing this introduction, I'd now like to go back to slides for a short while. Well, actually keep the lights on the blackboard because I think the slides are visible and I want to write some things at the same time. Okay, so these examples are obviously toy problems in the sense that they only involve a small number of spins. But they're useful toy problems because we can go to lattices which are built up from these units. And one way of building up a lattice from one of these units is by putting them together, sharing sites at the corners. And two famous lattices are the Kagame and Pyrochlore lattice, which are obviously built in 2 dimensions or 3 dimensions by corner-sharing triangles or tetrahedra. And so you can hope that some of this physics will carry over from the cluster to the full lattice, and I'll explain in a lot of detail how that happens. So then I thought I should mention some materials, and I've chosen 4 examples here, which I'm going to say a little bit about, and together I think they illustrate different aspects of the field. So this first material, strontium, chromium, gallium oxide, I picked partly because it was really the material that people first started thinking about when the field took off round about 1990. And actually at the time they thought it was more or less an example of antiferromagnet on the two-dimensional Kagame lattice. And in fact, although it's quasi-two-dimensional, it's probably better to think of it as being made up out of slabs taken from this pyrochlore lattice. But anyway, it's got spins on a frustrated structure, and the spins are in fact good approximations to Heisenberg spins with a magnitude s equals 3/2, which means that this system is probably quite close to showing classical behavior. And then I'll talk about spin ices, and this holmium titanate is one of the main examples. And again, that's built up out of spins on the pyrochlore lattice, and as I'll explain in the third lecture, we can think of these as being described by Ising variables. And then the other two materials that I'm going to talk about, Herbert-Smithite and Kappa-ET, are described by models with spin 1/2 on two-dimensional lattices, in one case the Kagame lattice, and in other case the triangular lattice. And so being spin 1/2, these are systems where quantum mechanical effects are very important. Now, if someone tells you about a new magnetic material, then one of the first things that you'd like to know is something that tells you about the interactions in the system. And in each of these systems, I've listed the experimentally determined Curie-Weiss constant. So in case there are people who are not familiar with what that means, let me tell you or remind you. So if we think about the magnetic susceptibility, then the Curie law would give us a susceptibility that varies with temperature as 1 over temperature, and that applies when you have no interactions between the magnetic moments, and when you have interactions, you have the Curie-Weiss law. And the susceptibility varies as temperature minus a Curie-Weiss constant. And this Curie-Weiss constant, if we have a single interaction scale in the system, is proportional to minus the interaction strength. So the point is that from the behavior of the susceptibility, at high temperatures where this Curie-Weiss law is accurate, we can find out what the interactions in the material are by determining the Curie-Weiss constant, and in particular from its sign we can find out whether the interactions are ferromagnetic or antiferromagnetic. And so you see that in this first material, SCGO, we have rather strong antiferromagnetic interactions with a Curie-Weiss constant of 500 Kelvin. We have much weaker ferromagnetic interactions in spin ice, and in these quantum materials we have rather strong antiferromagnetic interactions. So if you go further and probe the properties of these materials experimentally, well, you can look at what happens to the susceptibility as a function of temperature. And given the Curie-Weiss law, a natural thing to plot is the susceptibility inverse, which should be linear in temperature, and then from the intercept on the temperature axis, you get the Curie-Weiss constant. So there's two lots of data on this slide because the material naturally comes with some level of dilution. The chromium ions are the magnetic ions, and the composition of the material varies according to the value of x. So we get different data in the two cases. But the important thing is that we can extrapolate this high temperature behavior down, and it crosses the axis at temperature of minus several hundred Kelvin, showing that we have really strong interactions. But at the same time, we can cool down to temperatures far below the interaction scale, and the inverse susceptibility is a smooth function of temperature, suggesting that there's no phase transition. And in fact, if you zoom in at low temperatures, then there's some indication of spin glass behavior, but on a temperature scale of around 4 Kelvin, in other words, something like 1/100th of the basic interaction scale in the system. So there we have a consequence of the degeneracy that I was talking about with the toy example. We have fluctuations destabilizing an ordered state. To probe what is happening in the system at low temperatures, you can try and do diffraction experiments. Of course, if you do diffraction from a system of ordered spins, then you'd expect to see Bragg peaks. And what you see in these frustrated systems, instead of a Bragg peak, is a rather broad peak. And the width of the peak tells us something about short-range correlations. And so the fact that it's broad tells us that the correlation length that's being probed here is quite short. And then, importantly, you see that the scattering at small wave vectors is small, and scattering at small wave vectors tells us about fluctuations in the magnetization, the global magnetization. And so this tells you that fluctuations in the overall magnetization are suppressed. Well, if we have configurations of spins which are arranged locally so that the net moments are zero, then that's exactly what you'd expect to be happening. If you just look at diffraction experiments on a powdered material, which enables you to get the strength of scattering as a function of the magnitude of the wave vector, then you don't get the full story. You can't actually make this material SCGO in single crystal form, but if you go to the spin ice materials, then there are single crystal diffraction experiments, and when you instead of averaging over orientations, look at diffraction resolved by angle as well as magnitude of the wave vector, then you find that there's lots of sharp structure in reciprocal space. So although you don't have Bragg peaks, you do have structure which is sharp, and in fact in pretty good correspondence with theories which I'll talk about. And the fact that you have sharp structure in reciprocal space means that via the usual properties of Fourier transforms means that you must have some long-range correlations in real space, and part of the lecture on spin ice will be to explain how we can understand those correlations. Okay, so those are the two classical materials that I wanted to talk about, and I'll say a little bit about two quantum materials. Are there any questions at this stage? So I just want to mention in 2 slides some of the things that we look for when we look at quantum frustrated magnets and signatures of spin-liquid behavior. So this is data doing inelastic neutron scattering from this material, Herbert-Smithite, which is close to being described by the spin-a-half Heisenberg model on the Kagame lattice. So when you do inelastic magnetic neutron scattering, the idea is that the neutron loses some momentum and energy to the sample, and in doing so it creates some excitations in the sample, and you measure the cross-section for losing energy and momentum as a function of the loss. And if the main effect of the scattering is to generate single excitations in the material, then when you do that, you can track the dispersion relation for those excitations, and at a given energy, you see excitations only at particular wave vectors. So these pictures are slices in scattering, each one at a different energy, showing in a color code what the scattering strength is as a function of wave vector in two-dimensional reciprocal space. And the main point is that instead of seeing well-defined wave vectors with sharp scattering and no scattering elsewhere, you see scattering that's broad in wave vector. One way to understand this is if the neutrons, when they're scattered, generate not single excitations but multiple excitations, so that the energy that's transferred to the sample can be shared between several excitations, and a given energy can correspond to a whole range of possibilities for momentum transfer. So the significant thing in this data is that there's no sharp structures, and perhaps that's an indication of generating many excitations in the scattering. And then the final piece of data that I want to show is to do with a specific heat measurement on the second of these quantum materials, which involves spin-a-half on a triangular lattice. So if you think back to undergraduate facts about heat capacity, then in a metal you have two contributions to heat capacity, one coming from the electrons and the other from the phonons. So the electrons give you a contribution linear in temperature, and the phonons a contribution that goes like T cubed. And what's plotted here is the heat capacity divided by temperature. So we have a constant term, and then it's plotted as a function of t squared. So on this t squared graph, we'd have linear behavior. So if this data were for a metal, then you'd understand the intercept as just telling us about the coefficient of the linear contribution to the heat capacity from excitations of electrons near the Fermi energy. But the surprising thing about this data is that this material is certainly an insulator, and so we don't have any of the usual excitations that would give us a linear heat capacity, and the idea is that somehow the spin degrees of freedom are producing this contribution in a way that we perhaps don't fully understand yet. Okay, so I think those were all the slides. Yeah. Okay, so that's intended as a sort of overview of the direction we're heading, and now I want to go on to some more detailed material. Any questions about those slides? Okay, so now I'd like to carry on with these kinds of arguments.
Plot that you showed, which was broad, that was showing short-range correlation or short-range order.
No, well, short-range correlations and no long-range. Well, how do you mean the difference?
Because for example, in Ising model, the fluctuations are very short-range, are correlated at a very short length scale, even in the ordered phase, deep inside the ordered phase. Even though it is or only at the critical point, the correlation length is infinite. Both sides of the critical point, the correlation length is small. In that sense, the one side is ordered, so I will get a very sharp peak. But if I look at the correlation length, that is still very small.
Sure. So the important thing is that there's no magnetic Bragg peak. So there's no long-range order.
Yeah.
And then there's some short-range correlations.
Okay.
Yeah.
But is that also showing that the correlation lengths are small?
Well, there are some subtleties which are to do with how much information you can get if you only know the scattering strength as a function of the magnitude of the wave vector and not its direction. But if we assume that all of the information is in the dependence on the magnitude of the wave vector, then the width of this peak in wave vector gives us some measure of the inverse of the correlation length. So if correlations were shorter, this peak would get broader.
Okay.
So I mean, you can understand this peak if you assume that nearest neighbor spins are correlated.
Okay.
Okay, so what I wanted to do now is develop a bit further the things I was saying about degeneracies. But but instead of just talking about a toy problem of a single cluster, I'd like to talk about a whole lattice of spins. And first of all, I'll talk about the pyrochlore Ising antiferromagnet. So this means that I have corner sharing clusters of Ising spins on the right-hand lattice there. And since we're talking about discrete variables, we can discuss the ground state degeneracy by counting the number of ground states. Our picture of the ground states is that locally within each of the tetrahedra, we have 2 spins up and 2 spins down. And the first point to make is that there's an extensive ground state entropy. The ground state entropy is proportional to the volume of the system. And you can see this because if you have one ground state, then you can go to another ground state by, first of all, finding loops in the lattice along which you have alternately up and down spins. So if you look at the lattice on the right and imagine drawing some closed loop, then one link in the loop will go between 2 sites in a given tetrahedron, and then the next link will go between 2 sites in a neighboring tetrahedron, and so on. And if we choose these loops to have on them alternately up spins and down spins, then within each of those tetrahedra that the loop goes across, there'll be 1 up spin and 1 down spin, and so we can reverse the spins on the loop and leave the other spins in the lattice unchanged, and we'll get to a new ground state. And because we can find independent loops in different parts of the lattice on which we can reverse the spins independently, we have an extensive number of ground states. So the question we're asking goes beyond that. We'd like to know what the ground state entropy is. And the ground state entropy is something non-trivial. But there's a way of estimating it which is quite interesting and turns out to be quite accurate. And the estimate goes back to work by Linus Pauling, who didn't know about spin ice and was thinking about an analogous problem in water ice, and it's actually the analogy that gets spin ice its name. So if we think about one tetrahedron in this pyrochlore lattice, then by itself it has 4 spins, and each spin has 2 states. So altogether we have 16 states. And if we count ground states, then as I explained, we have 6 states. So the fraction is 6/16. So if we go to a lattice with n spins, then incidentally the number of spins is related to the number of tetrahedra, obviously, and because each tetrahedron has 4 spins on it, but each spin is shared between 2 tetrahedra, the number of tetrahedra is half the number of spins. Then the total number of states in the system is 2 to the power of the number of spins. And this is the stage where you make an approximation, but the approximation is to say that if we want the number of ground states, then we should take this fraction for each tetrahedron in the system. So the number of ground states is approximately the total number of states times 6/16 to the number of tetrahedra, which is the number of spins over 2. And so if you simplify that, we have 4 to the n over 2 inside, and so this is 3 over 2 to the n over 2. So what we're saying is that the ground state entropy is KB times KB times the log of this, or KB over 2 times the number of spins times the log of 3/2. So times the number of spins, or it's that much per spin. And that's something that you can see experimentally. So, of course, experimentally, we can't measure absolute values of entropy. What you can do is measure entropy differences between 2 states. So what you do in the first instance is measure heat capacity, but then by integrating heat capacity divided by temperature, you get entropy changes. And incidentally, you have to separate out the phonon contributions to the heat capacity from the magnetic ones, and we just want to focus on the magnetic contributions here, but that's all been done for us. And then at high temperatures, when temperature is high compared to the interaction strength, we know the entropy should be log 2 per spin. So what we should be looking at is the entropy change when we go from high temperatures down to low temperatures. And the value of the entropy change is given for us here. And rather than getting a loss of entropy when we cool down of log 2 per spin, or R, the gas constant, log 2 per mole, we find that the entropy loss is reduced by just this ground state entropy. So my point here is that the degeneracy, which comes from frustration, has consequences which you can observe rather directly in the experiment. that's half of the story when we're thinking about Ising degrees of freedom. But if we think about vector spins, then, as I explained, rather than counting ground states, what we should do is count degrees of freedom in the ground state, and that goes slightly differently, and I'd like to explain that next. Yes. Thanks. Well, sorry, this is an experiment.
So here I need to look at some sort of high plus Kelvin, that kind of temperature is where I think, so based on the kind of difference that I see compared to the paramagnet to the sort of low temperature that is kind of close to that entropy difference. I mean, is that what we need to look at? Because in the very low temperature, I hope it is going to some sort of order state, or that is.
Yes. So you can ask what about the third law of thermodynamics and so on. Well, I mean, this material doesn't, in practice, order at low temperatures, but the reason for that is almost certainly that it stops equilibrating at low temperatures. And you can ask what happens in simulations, and in simulations you have to work very hard to get it into thermal equilibrium at low temperatures, and if you do that, then, well, in the simplest model with only nearest neighbor interactions, there's no order even down to 0 temperature, but if you add additional interactions, then typically it would order.
So here in the second paradigm, you apply some magnetic field, so that will, I hope, lift the degeneracy, right?
So, yeah, so this temperature range goes from temperatures far above the interaction strength at the right to temperatures which are significantly less than the interaction strength on the left. And so what you're seeing is the loss of entropy when you go into this set of low energy states where you have 2 spins up and 2 spins down in every tetrahedron on the lattice. And I mean, in this system on experimental timescales, you don't see any extra contributions to heat capacity at lower temperatures. Yeah.
So with a finite magnetic field, could you replace the Pauling estimate?
Oh, sorry. You need a stronger magnetic field to polarize it at low temperatures, I think. Yeah, sorry, I should have found, I think looking at the magnetic field data just complicates the point I wanted to make. I should have found a graph with that omitted.
So this is Holmium type.
Yeah, I forget whether it was holmium or dysprosium. That's the message I wanted to get across. Yeah. No, I think it's a kind of mean field or cluster mean field result. But it's accurate to a few percent, I think. Well, in 3 dimensions, no, but for the analogous problem in 2 dimensions, you have exact solutions, and so you can make the comparison. And I forget exactly what the numbers are, but I think it.
But in 3D, I mean, somebody must have done some small clusters and tried to extrapolate, because the estimate you gave was just for 1 tetrahedron.
Yes.
2, 3, and so on. There must be some results.
Yes, or otherwise Monte Carlo results.
Actually, there was some work by Rajiv Singh
Mhm.
where they did some series calculations, but I think the answer was only slightly different from.
Yeah, it's more accurate than you would guess. Okay, so the next point I wanted to make was the analogous calculation to the Pauling estimate, but now thinking about systems with continuous degrees of freedom, where we should be counting the degrees of freedom in the ground state. So, in other words, n-component spins with n bigger than 1. And there's an approach which goes back to Maxwell, the Maxwell of electromagnetism, who was thinking about mechanical structures, but you can apply the same ideas to classical spin systems. And the basic approach is to think about the number of degrees of freedom in the system and compare that number with the number of constraints which you have to impose in order that the system is in the ground state. So if we ask how many degrees of freedom there are, well, if we have some number ns of spins, then if they're n-component vectors of fixed length, we have n minus 1 degrees of freedom for each spin. And in the case of the Pyrochlore lattice, I mentioned that we could count either the number of spins or the number of clusters. And if we're thinking about a lattice like the Pyrochlore or Kagame lattices, which are formed from corner-sharing frustrated units, then each spin is part of 2 frustrated clusters, and each cluster, well, if we have q spins in a cluster, each cluster contains q spins, so the number of spins is the number of clusters times q over 2. And if we think about the ground state constraints, then when I talked about the toy example of a single cluster, I explained that we could write the Hamiltonian as the square of the spin on the cluster, and the condition to be in a ground state was the constraint that the total spin in the cluster was 0. And on these lattices formed from corner-sharing frustrated units, we just repeat that idea in each cluster. So the number of constraints is the number of clusters, and then we have to constrain each component of the spin on that cluster to be 0. So we have little n times the number of clusters constraints. And then finally, what I'm heading to is the number of ground state degrees of freedom and if we can satisfy all these constraints and do so independently, if we just had a problem in linear analysis, the number of ground state degrees of freedom should just be the total number of degrees of freedom minus the number of constraints. So this gives us something which is proportional to the number of clusters, with the proportionality constant being n minus q on 2 times n minus 1. So if we take the Heisenberg model on the pyrochlore lattice, we have q equals 4 and n equals 3. So the number of ground state degrees of freedom is simply the number of clusters. So we have a macroscopic number of ground state degrees of freedom. And again, we can understand that that will destabilize ordered states and give us the possibility of some different physics. Okay, so in the final part of this lecture, I want to discuss concerns that you might have about simply suggesting that degeneracy should lead you to disorder. And in particular, I want to talk about an idea which is known as order by disorder, or you might phrase it better, saying it's about the possibility of fluctuation-induced order. Sorry, were there any questions there? Yes.
As the intercept is increasing with the field, so this indicates that the loss is increasing. So is there implications regarding frustration?
Sorry, was it that data you wanted? Yeah. Well, I think the most important thing to say there is that these are very much classical physics arguments, and this material is definitely a strongly correlated quantum system. So the rather naive arguments which I've been giving you won't help with this, with understanding this material. I mean, this is the heat capacity of a very much a strongly correlated quantum system. So counting states in the way I was doing is not going to help. Yes, it applies in generic states. I think what I'm about to say might bring to light a bit better what the issues are. Okay, so what I want to talk about is something known as order by disorder. Or you could call it fluctuation induced order. So the key point here is that the degeneracy that I've been talking about is accidental, and when I say that, I mean it in a technical sense. I mean, when you learn about degeneracy, for example, in quantum mechanics, you usually hear about degeneracies which are consequences of symmetry. And the degeneracy that I've been emphasizing, for example, as illustrated by the heat capacity of spin ice, is really not that kind of degeneracy. It doesn't follow from any sort of symmetry. It's a kind of accident of these frustrated systems. So, whereas degeneracy that comes from symmetry can be very robust, degeneracy which is just an accident is much less robust, and we have to ask whether it's going to survive fluctuation effects. So, at a cartoon level, the problem we want to think about looks a bit like this. We can think of the phase space for our system, and obviously if it's a macroscopic system, then the phase space is some high-dimensional space, not this two-dimensional drawing. And then within phase space, we have some ground state manifold, which is also high dimensional in these frustrated magnets. And if the system is not absolutely at zero temperature, then what it does is fluctuate around the ground state manifold. So the low T state is like that. And because the degeneracy is accidental and not symmetry related, the fluctuations are going to be different around one ground state compared to around another. And it could be that the fluctuations are much softer in some regions, and so the system near the ground state can explore a larger bit of phase space for one ground state than it can for the other. And so the question is whether these fluctuations can select particular ground states and lead the system to order. And if you try and think about that in detail, then you can imagine introducing some generalized coordinates. So we can have some set of coordinates that go along the ground state manifold and some other coordinates that are perpendicular to the ground state manifold. And you can imagine integrating out the fluctuations, so integrating out the fluctuations in the directions perpendicular to the ground state manifold. So if we had a single coordinate perpendicular to the ground state manifold, then we'd want to integrate some kind of harmonic oscillator coordinate perpendicular to the ground state manifold, and then we get something which goes like temperature divided by frequency, and for a single coordinate we'd have a square root. So if we have the high-dimensional system, just to give me some normalization for states in phase space. Sorry, that's possibly confusing. So I could have used, instead of h bar omega, some classical stiffness. So if you prefer, I have some classical stiffness in there. But the point I want to emphasize is that I get something which is large if the stiffness is small. So what I want to say is that if we integrate out the fluctuations around the ground state for a particular point parameterized by x on the ground state manifold, then I can get a weight on the ground state manifold as a function of position, which will be from integrating out these transverse coordinates with some classical Hamiltonian that depends on these coordinates. And the result will be, if I can do this integral in a harmonic approximation, it'll be a product over modes, and I have the frequency of those modes appearing in the denominator. And the key thing is that this weight depends on position on the ground state manifold. And so you have two possibilities. Either the weight might all be concentrated near some ordered states if particular states are preferred by fluctuations, or alternatively, it may be spread relatively uniformly over the whole of the ground state manifold. And in the first place, the fluctuations induce order, and in the second case, the system remains disordered even when you account for the effect of fluctuations. And to demonstrate those possibilities in more detail, I'd like to go back to the example of 4 spins on a tetrahedron. And And if we start with a ground state where the spins are all collinear, then we can think about a state which is not a ground state. And one example would be that we displace spins like that through some angle delta theta. And the ground state energy, as I said, is the square of the total spin length. And if we consider this particular distortion away from the ground state, then the transverse components of the spin still cancel, and we get a net magnetization for the cluster only because the horizontal component of this spin doesn't quite cancel the horizontal component of that spin, and likewise here. So we have a magnetization that grows like the square of the angle, and an energy which is the square of the magnetization, which goes like the fourth power of the angle. Whereas if I go to some more generic ground state, okay, so that's intended to be a ground state, and now I just change the orientation of one of the spins by some delta theta, and maybe this one by delta theta 2. Then the energy cost of doing that goes like delta theta squared. So the point is that fluctuations are softer around some specially selected spin configurations compared to fluctuations around a more generic spin configuration. And the question we need to think about in relation to fluctuation-induced order is whether the soft fluctuations around these special configurations actually lead to them being selected as the preferred states at low temperature or not. And you can work that out in detail, and I'll sketch how it goes and leave some of the calculation as an exercise. And you find that whether or not you get order from fluctuations, in fact, depends on the specific system that you're dealing with. And in this example, it depends on the number of spin components. So if we think about states of 4 spins on a cluster, then we can fix the configuration of 2 of the spins and allow all possible configurations of the other 2 spins. And we can work out a kind of partition function depending on the angle between the first 2 spins, which is just the integral over the orientations of the other 2 spins of the energy, and the energy here is just the square of the magnetization of the cluster. And then you say that the probability distribution for the angle between these first two spins is some normalization, and then it basically depends on the weight which we get when we integrate out these two spins times a volume factor, which is the usual sine theta for spherical polar coordinates if we're dealing with Heisenberg spins, or if we're dealing with xy spins with just a single angle, it's a factor of just 1. So the integral over these two spin orientations is something that you can do at low temperatures when you can treat fluctuations as just Gaussian, and it simply involves obviously parameterizing this integral. And I'll leave you to do that. But if you do it, then what you find is that the behavior of the probability distribution of this angle is quite different in the case of Heisenberg or XY spins. And you find that P of alpha is proportional to sine alpha over 2 for Heisenberg. And 1 over sine alpha for xy spins. And what that means physically is that in the Heisenberg cluster, all orientations, all configurations of spins in the ground state are possible at low temperature. Whereas in the case of XY spins, because this has a divergent weight at alpha equals 0 and alpha equals pi, you find that the spins are collinear as temperature goes to 0.
So this is the same as this. So here, so we said Heisenberg spins here sine alpha.
Yes. So Heisenberg is, of course, I mean n equals 3, and here I mean n equals 2.
So here we do have to get sine alpha, and then it's sine alpha.
There are two factors. There's the partition function from integrating out 2 of the spins, and then there's the volume factor from the relative angle of the remaining 2 spins. And when I combine them both, then I get this probability distribution. So this is an example applied to a single cluster. And when you go beyond a single cluster and to a lattice, then you find, depending on the example, you may either have order developing as you go to low temperatures, or the system may remain disordered as you go to low temperatures. So So the Kagame-Heisenberg model is an example of a system where you do get this order by disorder. And you, in fact, get coplanar spin configurations. At low temperature. And on the other hand, if you go to the pyrochlore Heisenberg model, then there's no order by disorder, and it remains disordered. As temperature goes to 0. Yes.
So naively, I would think something like Bernoulli should not allow any sort of order on this. But somehow, how do you get around Bernoulli?
You don't, but it gets increasingly ordered as you decrease the temperature. I mean, the correlation length diverges. Yeah.
So strictly at 0 temperature, it's when you have infinite correlation.
Yes. As you approach 0 temperature, it goes into it develops order. I mean, you need to ask how you introduce a measure over the classical ground states. And one obvious way of doing it is to take the Boltzmann measure in the limit temperature goes to 0. And if that's the way you do it, then you select ordered ground states. But you could sit down and construct some different measure, and there are lots of ground states which don't have this kind of order.
So here essentially t tending to 0 is not the same as t.
That's right, yeah. So, I mean, it's easier to think about in the case of a single tetrahedron where you can draw lots of ground state configurations that are not collinear for the XY model, but you select the collinear ones in the low temperature limit.
So effectively for these systems, if you follow the temperature dependence of the inelastic heat, you get extrapolated to equal to 0.
Yeah, sorry, you said of the... Yeah, well, experimental evidence for order by disorder is something that's quite delicate to discuss because you need to have a way of finding out whether there are additional interactions in the system which are responsible for the order. But you can certainly look for it in Monte Carlo simulations. Okay, I think I've used an hour and a half. I should stop there. Thank you. Yeah. Yeah, so these are thermal fluctuations, and you can ask similar questions about the effect of quantum fluctuations. It's much easier for quantum fluctuations to select ordered states. So for systems with large spin, when you're in the semi-classical limit, and it's easy to discuss these question starting from the classical description, then I think you expect that 0 point fluctuations will always prefer some specific set of ground states which will be ordered ground states.
Therefore, the Carbone-Hazelden model, as there is a ordered in co-planarity. So here we consider not the spin half type.
Right, it would be large spin, yeah, or really classical limit.
That's
Yeah.
why the for the OPGs major factor from here, not the quantum.
It's classical fluctuations that I was talking about there, yeah.
So if there are no further questions, then I think we should thank John for a fantastic lecture. So I just need to make one quick request to all the students. So our lecturers are extremely friendly. So I think you should make it a point to go and interact with them and talk to them and try to get as much as possible from these lectures. So please, I think you should interact much more. They are going to be around for the course of this for the course of this lecture series. So please do take advantage of them being around. So thanks. Thank you, John. It's nice. So there's a coffee break now for 45 minutes until, and we will assemble here at 11:30.